Hi, my name is Kevin Green, and I'm an undergrad research assistant in David Remy's Robotics and Motion lab at the University of Michigan. In the SURE program, I've had the opportunity to work on the control of our biped, RAMone. One thing you might notice is that RAMone doesn't have ankles. Instead, it uses racquetballs for feet. We use these instead of a large flat foot because we do dynamic walking. So there are two major ways to approach the problem of walking. Some robots, like Atlas, are statically stable. This means that at any point in time, they have their center of masses over their footprint. In other words, if they froze all their joints, they wouldn't fall over. That is by design a very stable way of walking. It does have drawbacks, mainly the maximum speed the robot can walk at and how efficient it can walk. Of course, this is based on the controller used, but often the design and the control of a robot are coupled together. For example, often static walking requires actuated ankles, which in turn makes the legs heavier and less reactive than they could be without. Other robots, like Mabel, walk dynamically. This means there are parts of the gait where the robot is falling or off balance. You can imagine if we're walking and have one of the legs in the air, we will be unstable on the other single point of contact. We want to walk dynamically because we believe that there is potential to exploit the robot's natural dynamics to increase walking efficiency. RAMone is especially suited for these experiments because it uses series elastic actuation. This means that the motors that are used to drive the hip and knee joints are not directly connected to the joint. Instead, there is a spring between the two. This should allow the robot to store energy at one point in a stride and release it later on. This is really similar to how the Achilles tendon stores energy in humans when we run. The hope is that we can explore how to use optimization techniques to find efficient gaits in this complex system. Here, we are running a walking controller proposed by Pratt in his 2001 paper, Virtual Model Control, an Intuitive Approach to Bipedal Locomotion. We will use this controller as a standard comparison when we work to develop an optimal walking controller. Here, the robot is controlling the height, angle of the main body, and its forward velocity. Here, we can see another advantage of using series elastic actuation. The springs between the joints change a torque control problem into an easier position control problem. To apply a torque with series elastic actuation, you just need to make your motors create a specific spring deflection. This force control allows the robot to operate even when the legs are disturbed from their expected positions or when there are external disturbances.
I personally worked on the development and debugging of this controller. Throughout the summer, I worked collaboratively on issues, wrote functions, and helped conduct trials. We started implementing this controller at the beginning of the summer and have now taken it to the point where it's fully functional. In addition to the hardware implementation, I've been working on a simulation in MATLAB. This serves the purpose of helping us identify inaccuracies in our model and gives us a way to perform further optimizations. With a good simulation, we can run many more optimization trials than we possibly could on hardware. The controller you see here is an unoptimized walk controller that I wrote. In working on this project, I've learned a huge amount about controls, dynamics, developing a MATLAB, and debugging systems. I'm looking forward to when we move on to running optimizations and continuing to implement more controllers.